Welcome back to the analysis of PDs. Um, what we have been doing so far, we have been studying the long-term behavior of a nonlinear evolution equation. So we'll continue our discussions on that. So what I'm going to do in the beginning, that I'm going to recall some of the things that we covered in our last discussion, and then I will set up you call the main objective for today's discussion and the discussion that we're going to have after today's discussion. And then what we will mainly do today is going to be the abstract theory to study what we call the long-term behavior of evolution equation. And in the next discussion we will be kind of studying some of the more concrete problems actually. So let's just start with I mean, if you remember, we said that if you have, for example, given a nonlinear evolution equation that goes like this, du by dt equal to, say, some operator a of u plus some non-homogeneity that depends on x, t, and say u actually, okay, with some initial conditions and maybe some boundary conditions are given too. Okay, initial conditions and boundary conditions are given too. So, in order to study the nonlinear, the long-term behavior or asymptotic behavior of such kind of evolution equations, we actually said that there are basically three possibilities. Okay. We said that we're going to study what you call the first category of the problems, in which there are really three kind of possibility for such kind of evolution equation in the terms of the long-term behavior. So the first possibility is that as t goes to infinity, u, which is say a solution, a unique global solution to, for example, this evolution equation, then there are three possibilities as t goes to infinity. U can be unbounded, okay, so it can be unbounded, so it's not controllable in certain norm, okay, in certain norm. The second possibility could be, in other words, that the u blows up, okay, in finite time, and you can't really study its long-term behavior in the Jennings terms actually. The other possibility where u is bounded in certain norm, okay, u is bounded in certain norm, but it does not converges to any function in x actually, okay, so it does not converges to any function of x in long run actually. So we saw one of the example, for example, we talked about the wave equation, okay. For the wave equation, we know that in the long run, okay, you're gonna have your solution to the wave equation. It converges to a function that oscillates actually. Okay, so it just converges to a function that oscillates. That is not really an equilibrium point of the wave equation. It does not converge to some function that oscillates. The third possibility could be that u is bounded, okay, in certain norm. U is bounded in certain norm, and it converges to some function in x, okay. Say call this function psi, okay. And this function, we're going to call this the equilibrium atom. Okay, so equilibrium. Okay, so in other words, the third possibility is that U is bounded, U is bounded and it converges to some function, some specific, function in long run. Actually, for example, we saw that if you're going to take, say, a heat equation, simple 1D heat equation, a 2D, 3D heat equation, and study its long-term behavior, it converges to, in long run, it converges to what you call a stationary solution of the problem, actually, or a stationary solution of the same problem, which is, say, for example, in certain conditions, the way we discussed, it converges to 0 in long run, actually. So my point is this, that for a given nonlinear evolution equation, you can have these possibilities, actually. And you can study these three possibilities in two manners. The one manner is that, okay, you study these possibilities for, say, for example, a fixed initial condition. Okay, so you can have one of the behavior of the solution to the evolution equation for a given initial condition, given fixed initial condition. The other possibility could be that, okay, if you consider, say, a bounded set of initial conditions, and then you want to study the long-term behavior of such nonlinear evolution equations, actually. So what we are interested in today, we are going to build some theory which will help us to deal with this third possibility, actually, that, okay, if you have an initial condition or a given set of initial conditions, actually, under what conditions, what kind of equations you should have, or under what conditions the global solution, the unique global solution to the function, to the evolution equation, a nonlinear evolution equation, converges to some equilibrium point in long run, actually. Okay, so this is what we want to do today. So what we like to do, we like to develop some abstract theory for it and then apply it to some concrete cases, actually. So this is what that we're going to do. We just recalled it. I mean, if you remember, we already covered some bits of it in previous cases. For example, for the reaction diffusion equation that we considered, that I'm going to write again in a moment. Okay, so the reaction diffusion equation with the cubic heat equation with the cubic nonlinearity. For this equation, we kind of showed that if you compute, say, the L2 norm of the derivative of the time derivative of the u, this goes to 0 as t goes to infinity. Okay, so we kind of, in our previous discussion, proved a lemma that allowed us to conclude this. Another interesting question would be that, okay, I know that the time derivative of this goes to 0 as t goes to infinity. How about u, actually? So can we say something sensible about u? Then, so this norm was, I think, L2 norm. Then we also discussed 2D Navier-Stokes equation, actually. Okay, and we proved its well-posedness, we proved its existence and uniqueness, and then we also studied its long-term behavior, and then we also showed that the LP norm of the global solution to the 2D Navier-Stokes equation goes to 0 as t goes to infinity, actually. Okay, as t goes to infinity. So what does this shows? This shows that, okay, the norm of, for 2D Navier-Stokes equation or even reaction diffusion equation, it shows that the norm of the LP norm of the solution is controllable, actually. Okay, so it does not explode; it goes to something specific. But the interesting question would be that does this solution or this solution to reaction diffusion equation converges to an equilibrium point, actually converges to a function that is equilibrium point, and how to determine such functions, and that will kind of give us a glimpse that, okay, what would be the behavior of nonlinear evolution equation actually. So what we like to do, we like to take this discussion that we had previously to a new level, and we want to build an abstract theory that will help us to study, what do you call, the long-term behavior of such evolution equations in long run. Specifically, what we will be interested in doing today, we will not consider a generic class of evolution equation, but we will consider a specific class of evolution equations which are called the gradient flows actually. So we will develop our sum of theory that will allow us to study the long-term behavior of the gradient flows, and you will see that a large number of very interesting equations basically fall in this category, so you can apply the methodology that we will develop to study the long-term behavior of nonlinear evolution equations actually. So this is the overview that we had previously. So what is objective for today's discussion and the upcoming discussion? So consider the following evolution equation. Okay, following evolution equation. Okay, so let's write it. So say, take for example a particular equation which is say nonlinear heat equation with cubic nonlinearity are the reaction diffusion equation. So consider this equation ut equal to gradient of u plus u minus u cube, where x and t, u is a function of x and t, they belong to some domain and r plus, okay, and u, where omega is say some domain in Rn. So for the sake of simplicity, we may assume that it's a bounded domain, okay, and n is less than or equal to 3, and we may also assume that gamma denotes the boundary of the omega of the domain, and this boundary is C infinity, so it's really a smooth boundary actually. So what more do we know about this? That it's a initial and boundary value problem. That the boundary condition that we have is that u on gamma is 0 and u of say x0 is equal to u naught of what you call x actually, where x is obviously from omega. So this is one of the problem. Actually, when we will define gradient flow, we will actually show that this equation is basically an example of a gradient flow actually. So this is what that we're going to do. So what we would like to do for this theorem, for this reaction diffusion equation, we mainly want to prove, we mainly want to develop some abstract theory that will allow us to prove this theorem actually, and that goes like this actually, that if you take any initial condition u naught from H2 intersection H1 naught, I hope you remember the Soderberg spaces, then there exists an equilibrium psi, okay, equilibrium psi that is smooth, okay, such that and that satisfies the stationary version of this equation, in other words, it satisfies, say, Laplace u equal to u cube, or Laplace psi equal to psi cube, say, minus psi, and psi on the boundary of the domain is 0, okay, and such that the global solution, okay, the solution to say, call this problem is star solution is star converges to psi in H as t goes to infinity. Okay, so as t goes to infinity, the solution, say u, converges to psi. In other words, that the u xt, u of t minus psi in H norm goes to 0 as t goes to infinity. So this is what that we would like to prove. So what we would like to prove, that if you consider we want to develop some theory, some methodology, some method actually that will allow us to prove this result. And what does this result is telling? That okay, if you have, say, a nonlinear version of a heat equation, okay, then for any initial data here, you can always find an equilibrium point or a stationary solution, smooth stationary solution, which satisfies the stationary version of this equation, and the solution u to this problem converges to some stationary solution in long run as t goes to infinity. So this is really our meta objective for this and plus next lecture actually. In this lecture, what we will like to do, in this lecture, we will like to study how do you call some fundamentals of dynamical systems, fundamentals of dynamical systems. In particular, we will focus on what we call the omega limit sets, which plays a pivotal role while studying the nonlinear, the long-term behavior of nonlinear evolution equation. We'll study in detail the omega limit sets and some of its key properties. We'll prove some results. Then we will study what you call the gradient flows. In fact, what we are going to do is that we're going to show that if you want to study the long-term behavior of nonlinear evolution equation, that evolution equation can be basically treated as a dynamical system. For that dynamical system means something, some process that evolves over the time actually. Okay, that evolves over the time, so you call that as the dynamical system. So the evolution equations can also be treated as the dynamical system. So what we would like to do, that if you have some evolution equation like this or like this, then and you want to study the what you call long-term behavior, the best place to look out for the equilibrium solutions, okay, the solutions of the stationary problems to which the solutions of the evolution equation will converge in long run, where we're going to find, or we can find what do you call those stationary solution to which the solution of the nonlinear evolution equation can converge in long run. The best place is study the omega limit sets actually. Omega limit set. So that's the set that you have to look for. So we'll study some of the properties for it, and then we will basically study the what you call omega limit sets for the gradient flows actually. Okay, omega limit sets for gradient flows and the long-term behavior actually. Okay? Long-term behavior. So these are the two things that really we would like to do today actually. And in fact, probably I'll end my discussion by showing that star equation star that we have, the problem star, is a gradient flow. Problem star is a gradient flow. In other words, the solution to the problem star is a gradient flow. Okay? And since you have abstract theory, that means that you can study the long-term behavior of the problem star by studying the omega limit sets actually. So this is what that we like to do. We like to focus on omega limit sets, what these are, okay, what are some their basic properties, then we'll focus on gradient flows, and then we'll focus on that, what would be the omega limit sets for the gradient flows and hence the long-term behavior. And then we will show that the problem that we have posed here is indeed a gradient flow. So this is something that we would like to cover today actually. So this is something that we would like to cover today. So let's start. Let's start. Let's start with some basic concepts. The results that I'm going to present here are going to be now on abstract, and then we will try to apply them into the, for example, say this concrete situation actually. And in fact, what you can do, the key problems that we have been and that I have assigned to you, you can also study their long-term behavior using this kind of theory actually, or using this theory. So this is one of the tasks that you have to do, that I have assigned some of nonlinear evolution equations to you to study. You have studied already their well-posedness, so probably it would be a good time to check that whether they are gradient flows. If they are gradient flows, you can apply this theory to study their long-term behavior. So let's just start. So what I would like to do is that let's just start with some of the basics of dynamical systems. Dynamical systems in its essence is a huge theory. Okay, and I'm not an expert in dynamical systems, so I'll just talk about that part of dynamical systems which is relevant to us actually, but that's one of the interesting areas. So what the dynamical systems is all about, dynamical system is all about is studying the processes that change over the time actually. Okay, for example, these days you have this trouble of the COVID-19, it's a perfect situation for the people who are interested in dynamical system to study the way COVID is spreading or dying out or causing harm through theory of dynamical systems actually. So all time-dependent differential equations, partial differential equations, initial value problems, you can treat them as dynamical systems actually. Okay, so let us fix some notation. For today's discussion, H is always going to be a Banach space. Okay, so H throughout is a Banach space, and assume that we have been given some evolution equation. For example, I wrote this evolution equation, say du by dt equal to a of u plus f of say x u, u naught of x actually. So I'm not being concrete about what is their domain and so on and so forth. So it's a nonlinear evolution equation actually. And let's assume that for this, nonlinear evolution equation, wherever I'm gonna write U denotes the unique global solution. So it's a unique global solution to the nonlinear evolution equation, for example, of this form actually. Okay? This form. The problem could be initial value and for the boundary value as well. What would be U naught? U naught for us is always going to be an element in H, and we're going to treat that as what we call some initial data. Okay? And S of t, by S of t, I'm gonna mean a C naught semigroup. So this is going to be a C naught semigroup. Okay, that does what? So it swallows the initial condition. So obviously it's a linear bounded operator from the Banach space to the Banach space actually. So it's a map from H to H that swallows the initial condition from H and it spits out the initial condition and it spits out what do you call a trajectory of the solution of say nonlinear evolution equation at time t actually. So obviously U naught is in H and U of t is also in some suitable space actually. Whatever that space would be, it can't be outside H actually, because we are living in what do you call this space actually. So by S of t, I'm going to mean what do you call by S of t, I'm going to mean the C naught semigroup. And as previously, we're going to alternatively use U of t as so sometimes I'm going to use U of t and sometimes I'm going to use say S of t operated onto U naught as the trajectory of the solution which starts from the initial data U naught actually. Okay, so we know that we can write by definition of semigroup we can have what we call such a relation actually, that U of t can be treated as an output of the initial data U naught under what do you call S of t. Okay, so this is one of the basic notation. And as I said that we are mainly interested in the case that as t goes to plus infinity and U, in other words the global solution of U stays bounded in certain norm in certain norm for some initial data or for some set of initial data. Then you know that there are various cases that the U can converge to an equilibrium point, okay, or it can get into some equilibrium state, or the other possibility is that it can't, it just goes into some kind of a state which is not an equilibrium. In other words, that it could be the situation like the wave equation that it just keeps on oscillating. It does not take an equilibrium state. Okay, so these are the what do you call possibilities that you can have for it. And as I said, we will focus on basically this. Okay, we will focus on this actually, this factor. Now, as I said, if you want to study, for example, the long-term behavior of such nonlinear evolution equation, where the global solution of it stays bounded in certain norm, then to study the long-term behavior, the key what do you call object or the place is to study the so-called omega limit sets actually. Okay? Omega limit sets. Let me define what do I mean by an omega limit set. So there are two ways to define omega limit set, and both are equivalent. Okay? So your exercise would be to prove that the both ways are equivalent. The first way